All right, let's start. Do you have any questions? Okay. So let's continue with the last two problems from chapter 3. Then we'll move on to chapter 4. The first one is question number 59. Which says that we have a collection of n coupons. And then each coupon independently is of type I. I was from 1 to, I don't know, right? Let's say R, with probability some PI is equal to 1, right? And what we want to compute, well, is probability AI intersect AJ, where, right, AI is the event that coupon I, type I, right, is in the collection. Okay. So the point here, right, is that this question is not that hard, but textbook asks you to do it in 3 ways. And so A, right, by conditioning on Ni, the number of type I coupons in the set. The second one is by condition on Fi, or which is the first time type I coupon is collected. And the third is just by the inclusion-exclusion formula. Okay. So the inclusion-exclusion formula, part C, right, is the easiest, because basically we said how, right, P of AI, type I is in the collection, really is just this, right? Because it's the complement of type I. None of the coupon is in type is of type I. Similarly, right, AJ is the following, right? This is what we're solving for. And then AI or AJ is in the collection. The complement of that is AI not and AJ not in the collection, meaning that all coupons cannot be, right, of type I or type J. Okay, so we'll get one second. Yeah, so you bring this over here, right? And then you subtract over here. Okay, so that's the answer. It's pretty straightforward. No, nothing crazy about this argument. But so the textbook asks you to do it by conditioning. And well, like I said, at first you might think that this is super strange, right? Why approach the problem using a, let's say, harder or more challenging approach? And that may just come from the fact that we don't do conditioning as much as, or we're not used to conditioning, right? As much as like just calculating probability, you know, straightforwardly. But when you really think about conditioning, or if you just really want to do this problem by conditioning, then you'll see that these two are actually quite natural, especially part A, right? Conditioning on how many coupons is of type I in the collection. It's really a natural thing to condition on. Now, part B, the first time something happens actually is part of a broader scheme of stochastic process called stopping time. So when we look at a stochastic process, as you'll see in chapter 4, the first time something happens will play a big role, okay, in analyzing a stochastic process. And as I also said, even though chapter 3, right, and maybe chapter 2 don't advertise themselves as stochastic processes, the problems they talk about are of that type anyway, because the process of collecting n coupons really is, right, a stochastic process, something random progressing in time. You collect the first coupon, the second coupon, the third coupon, so on and so forth, okay? Anyway, so here, it just really trains us in conditional thinking. And our goal, right, is not only to write down the answer, but also to make sure, right, that all answers agree, all right? And that's sort of like where the, you know, the time spent, right, is involved, because we really have to do the calculation to show that they're all the same answers. All right, so first, by conditioning on Ni. So here, right, you basically could say that this is the law of total probability. So you condition on Ni equals to what? Some values, right? And then multiply back with that probabilities, and then sum over all possibilities. But as I explained, when you think about it, the only possibilities that make sense are for Ni to take values from 1 to n minus 1. Because Ni is the number of type I coupons in the collection, right? If there's nothing, right, there's no coupon of type I, then clearly this probability will be 0, and there's no need to add it. If all coupons is of type I, then there's no coupon that is of type J. So this is also 0, so we don't have to add it, okay? So really it's just 1 to n minus 1. Okay, so now to work out this expression, we'll see that, right? So this is the easy part, right? To have k coupons of type I, then, well, that's a binomial distribution, right? With success probability being pi, right? So just n choose k, pi to the k, 1 minus pi to n minus k. On the other hand, right, here, what are we looking at? So here, if k coupons or k positions has been filled in, right? So k of these, let's say this, this, and this, these are already of type I, right? That leaves the remaining n minus k to be, you know, of type J, or we need to look at the possibilities of the remaining coupons to be of type J. But one thing to note, right, is that, so basically here, right, we need at least one of the remaining n minus k coupons to be of type J. So it might look like this calculation, right, which is really the complement of, you know, all remaining n minus k coupons, right, are not of type J, right? However, conditioning on, right, exactly k coupons of type I, and we look at the remaining coupons, mean that, right, the remaining coupons cannot be of type I. So we're in a conditional space where these coupons cannot be of type I. So really, right, this the universe now is reflected through that. So the coupons cannot be of type I. So everything is weighted with respect to that, not of type I. And that's the only thing that is, let's say, challenging about this part. Okay, but that's it, right? So 1 to n minus 1. So this sum right here would be the answer to part A. However, right, our task is not done here. Our task is to make sure that this sum is the answer in part C. Any questions so far? And so here we use the binomial formula, right? The binomial formula, right? So, okay, so first of all, notice that there's this sum, right? This sum, well, is n choose k. This plus this is 1. So it's like 1, right? But 1 missing the first term, which is the 0th term, and the nth term. So we need to subtract that away. So one of those 0th term would be pi to the n, and one of them would be 1 minus pi to the n. All right, that would be this sum. Any question? Now, if you multiply in, right, for this expression, you see that 1 minus pi to the n minus k get canceled. And so you're dealing with a binomial sum again, except that now the terms sum up to 1 minus pj, right? 1 minus pj. So that would be 1 minus pj raised to n power. But, right, the sum again misses the 0th term and the nth term. So we need to subtract that away. So because one of the term is pi, right, you will also have a pi to the n. And the other one is 1 minus pi minus pj. So it would be And this is sort of like the place where I kind of fumbled a little bit last time. Any question? And so, right, you see that this and this cancel, and then you have subtract, plus, minus. Sorry. Which is exactly the answer in part C. Any question? Okay. So now we have part B, right, to do. So part B asks you to condition on a stopping time, right? The first time type I is collected in the coupon. Of course, right, this first time runs from where to where. So this is your first quiz, right? So you're asked to do part B, where is probability of AIAJ will be, right, the sum AIAJ, right, condition on Fi times probability Fi equals to K. Now K runs from where to where? It's the first time, right, that coupon of type I is collected. So clearly it runs from 1 to n. And none of the possibility is excluded, right? All of them are viable for the presence of the ith coupon and the ith type and the jth type, okay? So, well, so what are these? Your task is to fill this in, right? So what are these numbers? This would be easier, right? What is that? Well, this is just a geometric, right, random variable with success pi. So it will just be pi to the k minus 1, right, times pi. 1 minus pi to k minus 1 minus pi. What about this? Sorry, Fi equals to k, right? What would this be? All right. So you know, right, if you name the coupons 1 to n, then here's the kth time. And this will be the first time that I shows up. You really have to read that information. What that means, right, is that type I cannot appear before time k, but it can appear after, right, time k. All right. But what are we after? We know that Fi is equal to k. So that means type I is already there, the kth coupon. So we only need to control the j being present in the remaining coupons. and it will be good. How do we do that? So here, you still do it by complement, right? By saying that it's a complement of type J not being in any of the remaining coupons, okay? But how do you write type J not being in any of the remaining coupons? Well, notice that if you know one of the coupon to be of type I, then you might do something like this, right? For the remaining coupons. That's type J not being in the remaining coupons. But it's not that simple, right? The reason is because you cannot treat the one before K and the one after K to be the same. The one before K, as we said, right, cannot be of type I because K is the first time type I shows up. Therefore, the one before K must be 1 minus Pi and then minus Pj over 1 minus Pi. Very similar to the one above, right? This is the one sample space where I is not present. And this raised to what power? This raised to the K minus 1 power, right? The previous K minus 1 coupons cannot be type I, but then also here we'll make it also not of type J. The remaining N minus K coupons is more straightforward. It's just 1 minus Pj to N minus K. And then what? And then we take the complement of that. And the sum from 1 to N. Okay, any question? Now, the amazing thing, of course, is that this term, this expression, is also equal to this. How? How is this equal to that? I mean, by that, I mean the whole thing, right? Oh, so here, actually, there's nothing much for us to do besides doing geometric sum, okay? A finite geometric sum. The first sum, as you see, right, is from 1 to N, 1 minus Pi to the K minus 1 times Pi outside, right? That's the first sum. And, well, geometric sum will be the first term, which is 1, minus the next term after the last, which is N, divided by 1 minus the ratio, which is 1 minus Pi, which, right, unsurprisingly, just Pi, cancel with the Pi, giving us that. So that's this sum. Any question? Now the second sum, right, is of course this. There are several things, right? The first thing is this cancel with that. So we really have to sum only the top, right, times Pi. So let's write that. So Pi outside, right? But we only sum over k, so anything that does not involve k can be factored out. So there's a 1 minus pj to the n power. That also goes out. So leaving us with, right, first of all, this raised to k power. But then there's also this raised to a minus k power, which is a division, right? Okay. Any question? So again, right, geometric sum. First term here is when k equals to 1. So it will be 1 minus pi minus pj over 1 minus pj minus the next term after the last, which is when k equals to n, and after that, so that's 1 minus pi minus pj, 1 minus pj raised to the n plus 1. Divided by 1 minus the ratio, which is 1 minus 1 minus pi minus pj over 1 minus pj. All right, any question? All right, so let's clean this up. So common denominator here, as you can see, 1 minus pj, bring it up, subtract over here is really just a pi, right? The numerator here is just pi, which will cancel with this pi. So that's canceled. But then of course, right, the denominator here, when you flip it up, right, the denominator, right, divided by a ratio is multiplied by reciprocal, right? This brings up, will give you 1 minus pj to n plus 1. So that's that, right? And then to deal with this, right, common denominator clearly is 1 minus pj to n plus 1. So we got 1 minus pi minus pj times 1 minus pj to the n plus 1 minus 1 minus pi minus pj to the n plus 1 over over 1 minus pj to the n plus 1. Okay. Let me see here. So this cancel with this. That's not what I want. 1 second. Oh, yeah, I'm making there's one mistake, right? This is raised to k power, but there's a minus 1 here, right? There's a minus 1 here. Okay. The minus k here is over here dividing. The n is here, but I did not take care of the minus 1. So I need to also divide by 1 minus pi minus pj. All right. So that's my mistake. So I would carry it over here. Minus pi minus pj, right? And so let's divide over here. Okay. So let's see if that helps. So the first thing, once again, right, this cancel. So this cancel here giving me 1 minus pj to the, oh, yet one more mistake, right? With common denominator 1 minus pj to n plus 1, this is 1 minus pj, right? Already 1 minus pj, so you only need to multiply with nth power, not n plus 1, right? All right. So this cancel with this cancel with this. So there you have 1 minus pj to the nth, right? And then this cancel with this cancel with this, giving you a minus 1 minus pi minus pj to the nth. All right. And that's this sum right here, right? This sum right here comes out to be like that. But you're subtracting it, right? So you see the final answer will be this minus this plus that, which is exactly the answer in the other two parts. Any question? So again, right, this whole calculation is, strictly speaking, not necessary if you just want to calculate out the answer. But on the other hand, right, it is necessary if you want to reconcile or make sure of the fact that all three answers are the same. Therefore, right, justifying that as long as you condition on some random variable that makes sense, the answer you'll get will be the same. Doesn't matter which one you condition on. Right, any question? Okay, so now let's look at number 63. So now this one says there are n types of coupon. So there are n types. So the type, so let's just say this, right? Equally likely to be collected. And also, right, independent of the previous types, right? Collected so far. So that's just right to say that if you have, let's say, 5 types, then let's say you have collected 1, 2, 1, 3, whatever, then the next one will still equally likely be any of these 5 types and independent of, right, the previous ones. Doesn't matter what you have collected so far. The next one will be a uniform, if you will, right? A discrete uniform from 1 to n. Any question? So yeah, it's almost like you just keep having like IID, right? So you can say this is like IID, discrete uniforms from 1 to n. Okay, like that. And what is the story? The story is that now you have a random horizon, right? Notice that the previous question in terms of stochastic process is a finite horizon, or it's a fixed horizon, if you will, fixed finite horizon, because you just stop, right, at time n. It doesn't matter what happens at the nth step, you stop, right, because you only collect n coupons. Here, it's a random horizon because I haven't written it down, but you say the problem says you keep collecting, right? until you have the complete set. All types are present. All right. So the time you stop is a random time, right? Because who knows how many coupons you have to collect before you have everything. All right, then what do? Well, you want to find the probability that there's only, so this is quiz 2, right? Find the probability that type I, right, only appears once in the collection. So, which is again, right, something a bit strange to think about, or you wonder why do you care? Who knows? But right, basically, so right, the point is that, right, in the process of collecting, right, say type 1 shows up, type 2 shows up, type 2 shows up, right? So in this sense, for example, type 2 doesn't appear only once, right? It repeats. But down the road, type 1 can also repeat, right? As long as you have not collected a full set of all types, then coupons, right, the types can repeat themselves. So you wonder if, right, along the process of collecting, there's some kind of coupon that's unique. Yes, unique here means only appears once in the collection. Okay. What else should we say here? There's a hint, right? Because this question is not easy at all if you just run through the scenarios. Because how many scenarios can there be, right? I don't know. I don't even want to think about the number of possibilities, right? There's just so many. So here they would say by conditioning, right? And this object should be familiar. On TI, the first time that coupon of type I is collected. Oh, so sorry, right? It's not. It's not. Sorry. It's not the first time. When we say first time here, what we're implying or we're looking for is how many coupons have been collected so far until type I appear. That's not what we're conditioning on. It's the number of types that appeared before type I is collected. Okay. So again, right, for example, let's say you are focusing on type 3, right? That's type I. So let's say you collect 4, 5, 1, and then 3. Then 3 types have appeared, right? And let's say there's a 4 here, there's a 1 here, there's a 5 here, there's a 1, whatever. Then 3 types have appeared before type 3 appears, right? Okay. So thing like that. Again, right? When you first see it, it's like a weird random variable to condition on, right? Because again, right? I mean, that's why I kind of wrote down the wrong thing to begin with, because it is usually more natural to condition on the number of coupons you have collected so far, right? Like the previous part, this guy right here, right? The number of coupons you have collected until type I shows up. But no, you don't want that. Here you want the number of types that appear for type I is collected. But in some sense, this is still like a random time. But it doesn't matter time in the unit of coupons. It measures times in the unit of types, right? So it has the advantage that doesn't matter how many times, let's say coupons 1 showed up, it only counts as one time, one type, right? With respect to this random variable that you are looking for, right? For example, you're focusing on type 4 now, then even if type 2 appears twice, it counts as one type, right? Like that. And yet again, right? So this should give you a hint on how to think about the problem in this way. And it's kind of like a very interesting way of thinking. And it's really the right way to do it. I bet that any of us, when we look at this kind of problem, okay, what we automatically do is we go through the coupons. First coupon, second coupon, third coupon, fourth coupon, fifth coupon, and see what type they are. Let's say type A, type B, type C, type A. That's what we do, right? We look at each coupon and think of the type. But this will turn out to be very weird or very hard to think about in terms of the problem, because the problem is really focusing on type, even though it says that type I only appears once. Okay. The reason is, again, you do not have any control on how many times the type would appear, right? Until something happens. But so what I'm trying to say, right, it sounds a little bit weird, but the thing is you want to look at the type itself as a random event, meaning that, say, type A, type B, and then type A again like that, right? What you're seeing is type A comes first, then type B, and then type A again, and then type C, and then type A. You don't really care how many coupons have been of type A the moment it appears, if that makes any sense. So in other words, right, this probability okay, will be, right, sum over condition on value of TIs, right? But TI can take on what kind of values? Well, from 0 goes to K, right? From 0, right, to N. Type I can be the first one to appear. So in that scenario, TI is 0. Type I can be the last to appear. In that sense, right? Sorry. So here should be N minus 1, right? Because, yeah, sorry, right? Because type I is the last one to appear, then N minus 1 types must have appeared before type I is collected. All right, so N minus 1. Okay, so far? And then, of course, right, multiply with probability TI equals to K. Okay. So let's see here, right? What are these numbers? Let's say, what's the probability that K types appear before type I is collected? How do we know that? What's the probability that K types appear before type I is collected? Okay, so again, right, the key to this question is about focusing on the type, not on the coupons. So for example, right, let's say k equals to 3, just to demonstrate the thinking process. So you want 3 types to appear, right, before type I shows up. Well, obviously there's something along the line of n choose k, because, you know, out of n types, choose k types to show up before type I. Okay, but well, once you identify 3 types, let's say, so let's keep with the letter, right? Let's say type I, let's say A, J, and K, right? These are the types that you want to appear before type I. What's the probability of that? Well, notice, right, among these 4 types, they're equally likely to take on any order, right? Meaning type I can be here, type I can be here, here, or here, with probability 1/4 each, because they're all symmetric, right? All these coupons are equally likely to be collected uniformly, independently. So therefore, right, in this order, type I will show up last. That's what it means to be so many types appear before I is collected. But type I showing up last, or type I showing up in any other position among these k types, or rather k+1 type, right, are equally likely. Therefore, this is 1/k+1. Any questions so far about that? What about this then? Type I appears once if you know that k types has appeared before type I. Well, what does it mean? Well, so type I only appears once. So by the way, right, notice that when we write AJK like this, what we really mean, right, is that coupon A can appear so many times. We don't care. And then J, in fact, right, the J can come before, and there's a K, and then the I, right, like that. It doesn't matter how many times the coupons of types AJK appears, they can appear before type I. As long as 3 types appear, then the probability is 1/4. That once you identify those 3 types, then the probability is 1/4 that I will come last among these 3, right? Because 4 coupons types, I will come last with probably 1/4. Okay. So same thing here, right? Once you identify I, then for it to appear only once, what that means is the remaining types, right, must show up here. How many of them? N minus k, right? N minus k types. 1 second, right? It's not, is it N minus k types? N minus k minus 1 types, right? Because there are k here, there's I, right? So it's N minus k plus 1, if you will, right? Is that k plus 1, right? So among the remaining k plus 1 types, I must come last, right? In other words, if you now look at the ranking among the remaining types and I will have to come last again. But you see, this is just like a thinking process, because the moment you collect all these types and you don't care if I show up again or not, But pretend that you keep on collecting, right? Then the ith type must come last before those remaining types. What's the probability? That will be 1 over this plus that number. But this plus that number is 1 over n minus k. So there you have it. That's the answer. Any questions so far? All right. So part B of this question should be easier, which says that find the expected numbers of types that appear exactly once in the collection. So in the previous question, right? So this is sum over k, right? K equals left. In the previous question, what we did is we found the probability that a particular type, type I, appears once in the collection. Now we want to generalize that to, not generalize it, but now find the expected number of types that appear only once. What's the answer? Well, this one is easy, right? Because the answer here will be n times the answer in part A. Why? Because if you let xi, right, be the indicator function that type I appears only once, right? So 1 if, right, 0 otherwise, then the number of types that appear exactly once exactly is a sum of these guys, right? Over all types. That's what we're interested in. And of course, we've seen this question so many times. And these being indicator functions, there will be, right, equal to a probability. And all probabilities will be the same for any type because they're symmetric. So the final answer is n times that. Let's put n choose k here. Any question? I wonder if this becomes some kind of nice scenario where I don't care for the simplification. But there seems to be some simplification going on here. All right. Any question before we continue to chapter 4? All right. So let's continue to chapter 4. Markov chain. So let's talk about, so 4.1 is the intro to Markov chain, but I want to talk about 4.1, which is not Ross's 4.1. I just want to talk about stochastic process in general. Just so you know what the goal of a stochastic process is and what we do when we study stochastic process. So first of all, right, the most general definition of a stochastic process is a family of random variables indexed by time. And time here is really, in mathematics, it's just a directed set. What is a directed set? It means a set with a direction, meaning that, you can say that a number in the set is definitely bigger than another number, right? 1, 2, 3, 4 is a directed set, right? The real number is directed set, the natural number is directed set. So basically, if you want, right, the two most popular example is if time is discrete, right? Like the natural number, 0, 1, 2, etc., right? Meaning that the representation will be x sub 0, x sub 1, x sub 2, right? So the random variable is denoted by x, indexed by time, right? This will be called a discrete time stochastic process, right? Even though, as you see, the word stochastic process, the word process usually is more referred to continuous time. But, and if time is continuous, right? And by the way, so there's just a lot of distinction here. So it's probably impossible to say it all. But you don't have to get time to be infinite to keep on going like this. You can stop time at 10. In that sense, you have like a finite horizon stochastic process because you don't keep on going forever, like the coupon collection, right? With 10 coupons or with n coupons. But if you can keep on going indefinitely, then you might have an infinite time horizon. That's a time horizon, right, idea. But time is continuous, right? And the reason why I bring it up is because it can be finite time or it can be infinite time, right? But anyway, it's a continuous thing. Then you have something like x sub t, right? Like this or like that, which is a continuous time stochastic process. All right. So the point is, you see, from this point of view, I keep emphasizing that we have been talking about stochastic process. Okay, when you do coin flip, when you do coupon collection, when you do team, right, playing against each other, those are stochastic process. We just don't really say it out loud that they are stochastic process, but they are, right? So another thing that you want to pay attention to is the state space, meaning that where does the random variables, right? Where do the random variables take value? Okay. So these are random variables, right? As you may recall, you have at least, right? I mean, two types of random variable: the discrete random variables and the continuous random variable, right? So the discrete and continuous will refer to the values of the x, right? So in other words, you could have a discrete time, but continuous state space. You have continuous time, but discrete state space. So, right, time, state space, and maybe some example, right? If time is discrete, and state space is discrete, then you have a Markov chain. The word chain here, right, refers to discrete state space. An easier example would be something like a random walk. Okay, and by random walk we mean, right, you guys probably have seen it. You start a position, you would go left or go right with some probability, and you keep continuing that process, right? So X may represent your position at time n. You clearly see, right, that time is discrete there. State space is discrete because the positions, right, are discrete. You can have discrete time, but continuous state space maybe. Example of that? Not so sure. Discrete time, continuous state space. Not so sure. But there should be example of that. But if you have continuous time and discrete state space, then some very popular example would be some kind of queuing model. Because, right, people line up, okay, to get service. You would look at how many people are there in the queue. That's discrete. But, right, the time that they wait in the queue would be a continuous time. So that's why the queuing model would work. Famous example, well, it doesn't have to be a queuing model, but a Poisson process would be along this line, right? You have continuous time. Like, you can look at basically people arriving, right, at Macy's, as we've been looking at so far. But what we have been doing is we only looked at the number of people arriving within 1 hour. We don't care for when they appear, right? But if you keep tracking, let's say, the clock, and each time a person, right, arrive at the store, it jumps once, something like this, right? Time, right? And then this is the state, right? You start at 0 because initially you have no one to come, and then 1, and then 2, and then 3, and then 4, right? So on and so forth. And as you can see, right, I'm just drawing a very basic example, but this is like a jump, right, process. And you see, right, and of course, people can leave as well. Here we assume that we only count the number of people arrive, right? So notice the gap here, right, is random, representing, right, the inter-arrival time is random, can be short, can be long, but each time the jump is 1, representing 1 person has arrived at the store, etc. Right? So continuous time, discrete state space. You can have continuous. Well, I think it's just called stochastic process in general. But an example would be a Brownian motion, would be an example of continuous time, continuous state space. Okay. Of course, like I say, majority of the time we'll spend in this class, we'll do Markov chain. We have any time left, we're gonna move to queuing model, Poisson process. Won't do this in this class. Math 485 at Rutgers will touch on this from some other point of view. Again, can't really think of an example here. So, but there might be some stochastic process with this. All right. So, okay. So, yeah. Sorry, I'm still a little bit obsessed about this, so that's why I'm thinking. One thing that could happen here is you could subsample, right? For example, you take the Brownian motion and you just look at the position of the Brownian motion at discrete time point, then you may have something like this because, you know, the Brownian motions, they have continuous time space. So let's say something like a sampling, right? In time, right? Of a continuous stochastic process. So you have something continuous in time, continuous in space, and you just sample it at like discrete time points, and you will have a discrete time process with continuous state space by definition. Anyway, right. So these are just some general description on what a stochastic process is. But when it comes to this, right, what's the main question, let's say, or the number one goal? It's very hard to say what the main goal is because, I mean, there are so many questions you can ask, right? But if you kind of draw back to random variables, there's just so many questions you can ask for random variables, right? Expectation, variance, blah, 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 blah. But if you note, right, in the abstract, it all boils down to, let's say, the distribution of the random variable that you're interested in, right? Directly or indirectly, that's what you're doing. You're looking at the distribution of a random variable. So with the stochastic process, it's the same thing, but it's called the finite dimensional distribution. Meaning, right? And so meaning that for any stochastic process, what you want to be able to say is, if you want to know the stochastic process completely, then you want to be able to tell this following probability. Xt1 being in some set E1, Xt2 in some set TE2, etc. Xtn in some set En for all T1 up to Tn as a subsample of your time set. And then for all E1 up to En, let's say as a subsample Rn. So it's a very abstract writing, but what are we saying? In English, what we're saying is you need to be able to tell the joint distribution. This is called a joint, okay, of the state of the stochastic process at any finite sampling of time. Okay, so for example, right, let's go back to, let's say, the random walk example. Then the random walk, right, says that Xn is the position of the random walk at time n. Then let's say that in theory, if you say you understand the random walk completely, then you must be able to write down, for example, something like that. Again, I'm just writing something down, right? But what it means is, right, clearly, right, this is just a probability statement. What's the probability that at time 2 you're at position 4, time 4 you're at position 2, and time 10 you're at position 12? Can you say what that is? Of course, you can replace that into less than or equal to 4, equal to 2, whatever, right? It's really, this set can be quite arbitrary. But notice that here you're really talking about the joint behavior of the second position, the position at time 2, position at time 4, position at time 10, right? And notice for random walk, where you are, where you were at a previous time point, will influence where you will be, right? And so this is a complex question to answer. But finite dimensional distribution is what people are after. Or again, at least in theory, what people are after when they look at stochastic process. Any question? Okay. Now, but in reality, okay, direct answer to this is hopeless. I mean, unless in the abstract again you write down something, people use different techniques, okay, to simplify this question down. For example, right, you see in chapter 3 again, right, when you look at something like, I don't know, the probability that, right, the type I and type J is present in the collection. This is really some sort of joint behavior, right? If you look at all the position in n steps, you ask what's the probability that it will be in state I and state J at some point. And again, right, you see that's a joint behavior, right? We look at the entire path and you ask what's the probability that the path, right, will be a type I or type J and type J. But the technique, as you see, right, doesn't really invoke the joint distribution of all n steps directly. Because if we do that, it's hopeless, right? Even with conditioning, it's already kind of hard to do the calculation. So stochastic process study is really about how to different techniques to simplify this question down to something manageable, okay? And even assumptions we can make to make this calculation easy. And so keep that in mind when we do Markov chain and things like that, or let's say, right, Markov property. Okay. So first of all, right, because we are, right, having a stochastic process indexed by time, which is directed, there's this idea of present, future, and the past, right? And present is just whatever you choose to analyze at the current moment. So let's say present is time t, 1, 2, 3, 4, 5, whatever. Future, right, is anything above t, bigger than t, right? And the past, of course, is anytime before t, right? S less than t. So of course, associated with each of these time is a random variable or many random variables. For example, x sub s, x sub t, x sub u, right? Representing the state of the stochastic process right now, before and after. Markov property says that condition on the present, future and past are independent. Again, right? I mean, this is probably not what you hear in Markov regarding Markov property. So we'll state a more similar, right? A more familiar definition. But this is something that you may also want to hear. That again, this statement is quite complex, right? It's not that future and past are independent. No, right? Because if future and past are literally independent without any condition, then you might be looking at white noise, which means an IID process, independent, identically distributed random variables, okay? Fine, but those are very not interesting because there's no pattern to them, right? Even a random walk, right? Again, the future and the past of random walk are not independent, right? Because future position depends on the past position. However, right, condition on the present, meaning knowing the present, then the past and the future are independent. In the random walk context, what does that mean? Suppose you know where you are right now, right? You know your current position. Then the future, right, clearly only depends on where you are at the present. It doesn't really depend on what the past is. Yes. And the past, right? Again, notice, right? You only know where you are right now, right? You don't. So, for example, you know at time 4 you're at position 2. That doesn't tell you that at time 2 you were at position 4, right? You don't know that because that's not what you're conditioned on. So, but if you know at time 4 you're equal to 2, then where you will be in the future and where you were in the past are independent of each other. Does it make sense? Because I mean, you can kind of, with run and walk, you can kind of think of it like you can just reverse time, right? And start walking backward from time 4. Then, it's going to be independent, right? From that point of view. It will only depends on starting with at time 4 and go backward and go to time 10 is forward. So anyway, right? So that's one way to state Markov property. Another way, right, which is the more common statement that you'll see, is that only, right, when conditioning on a, let's say, the past history, only the most recent matters. Okay. What does this mean? So let's take discrete time point because, well, doesn't matter. For example, let's say, right, again, in the context of the random walk, let's say you want to look at probability that x10 equals to 12, condition x4 equals to 2, and x2 equals to 4. This will be if you have Markov property. Or later we'll say if Markov, this will be just this. Okay. And you can even have more. So for example, x10 equals to 12, x9 equals to 8, blah, 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 right? x5 equals to 12. Condition x4 equals to 2, x3 equals to 1, x2 equals to 4, x0 equals to, I don't know, 11. So you can have a chain like that, right? Because again, it's about joint distribution. So you don't have to have just a one single state. You can have the whole future path, right? Future path. Condition on, let's say, the past path, past trajectory. And you see, right, the future you cannot touch because that's what you want to calculate. But the past, if you have Markov property, you can safely drop everything before time 4 because that's what matters. Like that. These two probabilities are equal. This and that, if you have Markov property. Any question? Okay. So now, Markov property, right, keep in mind, is an assumption, or sometimes it's a deduction based on some other assumption. Just like independence, right? Independence is an assumption. Sometimes you derive independence from some other assumptions. But what Markov property does is that it will simplify the joint behavior calculation, or the joint behavior, yeah, right, the joint behavior calculation for you. So Markov property, right, let's put this down. Simplifies, literally simplifies, but I want to put in quote because simplifies here is not a precise thing, like something we can define. Simplifies, right, the calculation of finite dimensional distribution. Okay, let's see why. So again, right, let's maybe take that example. Probability x10 equals to 12, x4 equals to 2, x2 equals to, let's say, 3, right? This is a path probability, right? The probability of the path that goes through the states 3, 2, and 12 at times 2, 4, and 10. Now, if you recall, right, by conditioning, because now we have past, future, and present, whatever. Yeah, past, future, past, present, future. You can condition like this, right? And then you can further condition. Okay. So normally the state of things is like this, right? You want to know this path, right? Then you need to know how likely you are to start at the first time. And then you need to know how likely you transition from the first time to the second time, 2 to 4, with those. And then you need to know how likely you, sorry, I skipped, right? x4 equals to 2. How likely you are to transition from those two initial positions to the last position. Sorry, again, right? x10 equals 12. Okay. So this is the natural state of thing. This is always true, at least with this example. But what Markov does is it will simplify the middle step for you, where it will tell you that, well, because only the most recent matters, you can drop this. And again, right, this is what people intuitively would write down. To go from, right, these places, they will say start, and then move from 3 to 2, then move from, sorry, 12, right? Move to 12, 2 to 12. But, right, this is wrong in general, or with our Markov property. Because, right, history might matter, right? Something might not only depends on the most recent state, but it might depend on the whole history of how things evolve. If you encounter those things, then you cannot drop, right, the conditioning. But there's so many examples of Markov property out there. It's just so popular, so common as well, that sometimes or a lot of times people do this and they happen to be right. That doesn't mean that they're always right, right? So again, right, this kind of thinking where you move from one times to another, and then just, you know, keep considering your present position, that's due to Markov property. But as you can see, right, it greatly simplifies the path calculation, the path probability calculation, or as I say, the finite dimensional distribution property. All right, any question? So so now, right, let's write down what a Markov chain is. Well, not much, right? So basically a Markov chain has finite time, discrete time, right? Meaning time start at 0, 1, 2, etc., right? And time will usually be indexed by n. So n, right, are the time. N, k, m, that kind of thing, right? Are the time index. Discrete space, we I guess don't have a notation for it. So the space, well, for lack of imagination, will also most likely, or a lot of times, displayed, right, by integers. Okay, like again, think of the random walk, right? But this is the position 12 at time 10, right? Things like that. However, right, so time most of the time will not be capped. Time will keep flowing. But with space, you want to distinguish the finite space, meaning that space will have, like, there are only so many states, like 0, 1, 2, 3. So it's a Markov chain, right, that only revolves around 4 states. And I think it's right, students' favorite activity to draw arrows with some, weights, right? Describing the likelihood to move from one state to another, etc., like a graph, right? In fact, some sort of graph analogy will show up when you look at Markov chain. So, but that's finite state space. You can have infinite state space, okay? You can have infinite space. So, which means that the state space will keep on going forever, right? So what's an infinite state space? The random walk, right? The random walk, if you start at one position and keep going right and going left with some probability, there's really no cap, right, on where you can move. So keep this distinction in mind, because we will start out looking at finite state space, but we'll move to random walk pretty soon, which will have infinite space, and just the representation might be a little bit different, right? But anyway, so that's Markov chain. So with Markov chain, right, because so it's a stochastic process, right, with discrete time, discrete space, together with Markov property, right? Therefore, what we really are concerned with, or what we really want to know, so the path, right? Let's say, okay, maybe let's back up a little bit. We encapsulate, right, the transition probability. Let's call this a one-step transition probability. One-step transition probability as Pij as the probability that you will move to state J starting at state I. Okay? And this is for all n. And so it's just a notation, but Pij, right? So first of all, here's the thing. When you call Pij and you throw away the n, there's something here you want to pay attention to, even though it's so routine that maybe people don't really register it. There's some kind of time homogeneity here, right? Meaning that at every times, right, every time, the transition probability doesn't change, okay? But you can imagine, right? So the transition probability, if you will, only depends on the state, right? How likely you move from one state to another, right? Again, but I guess back to that graph analogy, right? Let's say you have 1, 2, and then let's say 3. 1 can go to 2 with prob 0.8, 0.2, and then 3 go back to itself, right? With prob 0.5, go to 2 with prob 0.5, whatever, right? When you draw this graph, what you're saying is that you move along these states with this kind of likelihood, but you would not even think about, right, the possibility that this may change as time goes on, right? Which is fine, which is really the context we're discussing here. But I just want to point out that it's entirely possible, right? As time moves on, that, this probabilities change, right? Which is not the context that we'll be dealing with, but it's worth pointing out that that's under the assumption. But so this is, right, Pij, P sub ij, right, denotes our transition probability. And many of you probably have seen this, right? It will, hold on, do we count the state from 0 or state 1? I don't, let me see here. Doesn't really matter, but time starts counting from 0, I'm pretty sure, but state starts counting from, I believe, state 0, yeah. And then let's say, like that, okay? So it's a n by n matrix if you have n states. And this is exactly where you want to pay attention to whether you're in finite space or not. Because if you have infinite space, Markov chain, then yeah, technically you still have a matrix, but it's an infinite matrix, which is fine, but it's not really that kind of matrix you see in linear algebra, let's say, right? So, and then, right, the movement, remember, right, is from I to J. So you move from row to column, right? That's the convention. You move from row to column. You move from row n to column 0. You move from row n to column 1, etc., etc. And so this is called the transition matrix. Rather, right, it's a one-step transition matrix, right? Any questions so far? And sometimes, right, sometimes writing the transition matrix itself, right, one-step transition, is a challenge, okay? Forget doing anything else. Just writing down the one-step transition matrix can be a challenge. So, well, the one thing, the one challenge with this Markov chain is the problem is a mouthful to write down. Well, but let's do it anyway, right? This is quiz 4. Let's say this is Gary's mood. You can have cheerful, ouch, cheerful, and then so-so, state S, and then glum, state G, okay? If cheerful today, then we'll be in CSG tomorrow with probability 0.5, 0.4, 0.1, if so today, and we'll be in CSG tomorrow with probability 0.3, 0.4, 0.3. If Glum today, we'll be in CSG tomorrow with probability 0.2, 0.3, 0.5. Let XN denote Gary's mood on day N. Okay, denote state 0 as C, 1 as S, 2 as G. Write down the transition probability. Write down the transition matrix. And when we say transition matrix, right, we mean by default the one-step transition matrix. All right, what would it be? So it'll be a 3 by 3, right? Matrix, where I think everything's already lined up for you, right? Because just the way it is. So nothing here, right? But it's just still worth to maybe write this down once, right? So you see. Okay. So again, notice what's the feature here. The feature of a transition matrix is what? The sum across the rows would be 1. Okay, why? Because from any state, you must go to another state. So the sum over the rows will be 1. Does the sum over the columns have to be 1? Nah, right? Why? Because, well, what is the sum over what does the sum over the column represent? Well, here, right, it's going to be the probabilities going into state 0, okay, starting from different states. How to say this? You don't have to go to state 0 starting from all different states or whatever. Basically, this sum doesn't have to be 1 because, right, that concept, that logic, right, of looking at all probabilities going to state 0, going into state 0, right, from starting from different steps, it's not even, basically, they're not even coming from the same universe, right? Because each of the conditioning gives you a different starting point to begin with. Okay, so that's the transition probability. Anything else do I want to say here? Yeah, not much. But yeah, any question about this? All right, but so that's just a simple, right, example, nothing there. Let's look at a more complex one. Quiz 5. So you have sort of like the rain, not rain scenario. Okay. So basically, suppose that you want to track, right, whether it rains or doesn't rain. And then here's a statement, right? Whether it rains or not today, depends on the previous 2 days. Okay, emphasis previous 2 days. So it says this: if it has rained for the past 2 days, then it will rain tomorrow with probability 0.7. Rain today, but not yesterday. Rain today, not rain yesterday. Then it will rain tomorrow with probability 0.4, 0.5, doesn't matter. And then yesterday, but today, rain yesterday, but not today. I guess you understand what that is now, right? Then it will be tomorrow with probability 0.4, not last 2 days, and it will rain with probability 0.2. So the point is, right, compare this with the previous question. You see that the previous question is a typical, right, way that Markov chain gets described. Whatever today state is affects tomorrow state. Here, whatever the previous 2 days is affect tomorrow. So question, is this a Markov chain? Or rather, right, maybe the precise question is, can we somehow look at this as a Markov chain? And if yes, write down the transition probability. If no, explain why it's not a Markov chain. What's the answer? Is this a Markov chain or not? Well, if you go with the sort of the English word, right, that only the most recent past matter, then you may think, right, that this is not a Markov chain because somehow it depends on 2 previous states. On the other hand, right, even within that English word, the most recent past, it doesn't quite say, right, the most recent past, right? Is it what I wrote there? Or did I write something else? Yeah, I say the most recent, right? It doesn't say the most recent has to be a one-time unit, okay? The most recent may be a 2-time unit, like this. So sort of like if you want to encapsulate this into some sort of like rule of thumb, and by rule of thumb here, I mean something I tell you that tends to be true, but I'm not responsible for it being true universally, okay? But the rule of thumb is if you have a fixed length history, dependence. What do I mean by that? So you could have the stock price tomorrow depends on the entire history of the previous month. By previous month, I mean the most recent 30 days, okay? As long as every single day depends only on the previous 30 days, counting from that day, then that's what I mean by fixed length history dependence, then it can be turned into a Markov chain, all right? You have to kind of relabel things. But, right, if somehow the history gets evolved, like suppose that the stock price tomorrow always depends on the history since, let's say, the opening of Dow Jones or something. Meaning, as time progresses, the history dependence gets more and more. Then it should not be a Markov chain, right? Anyway, so here the point is yes, right? It can be. You have to kind of be a little bit, let's say, sophisticated, right, in renaming things. How do you do it? Notice, right? Things only move from 4 states anyway, right? So you can denote something like this. State 1, state 0, if you will, is not rain, on the two consecutive. So basically, you model two consecutive days at a time. All right, you keep track of 2 consecutive days weather instead of keeping the weather or the rain, right, status of a single day. You track 2 consecutive days at a time, and that's actually a theme here, right? In Markov chain modeling. And by the way, right, just as this class has been so far, things will not be formulaic here at all. You will have to really actively think about what you want to model and how and why. So one thing, right, I just kind of said is you have to decide what are you tracking? What are you modeling? So again, right, for example, in this problem, modeling a single day rain status won't work because it will depend on the previous 2 days. But if you model 2 consecutive days, then it will work, right? So 1, let's say, is rain on the previous day, but not rain previous day, rain today. 2, swap that, rain the previous day, but not rain today. 3, rains on both. Okay. So let's see if you can write down the transition probability with this. All right. For example, right, what's 0 go to 0? 0 go to 0 means you must have this sequence, right? Meaning, right, that in the statement is like rain for the past 2 days and not rain tomorrow. So that's 0.3. 0 goes to 1. 0.7, right? 0 goes to 2. impossible. Again, notice, right, the row sums up to 1. So in fact, right, you can already conclude that it must be zeros, but you should also try to look at, right, the impossibility from the labeling. So 1 goes to 0 is impossible. 1 goes to 1, impossible. 1 goes to 2, not rain yesterday, rain today, then not rain tomorrow, right? So 0.5, 0.5. 2 goes to 0, rain yesterday, but not today, right? And then not rain tomorrow, so 0.6. 2 goes to 1, rain tomorrow, rain 0.4. 0, 0. 3 goes to 0, impossible. 3 goes to 1, impossible. 3 goes to 2, rain yesterday, rain tomorrow, 0.2. So this is 0.8 and 0.2. Any questions? Now, this question is from the textbook example 4.4. But if you look at their transition matrix, or if you look at the answer from the textbook, you'll see that they have a slightly different transition matrix than I do. What's the reason? The reason is, right, the states that I named here and the states that they name are not the same, right? And so we have different transition probabilities, but who cares? As long as, you're free to label whatever you want, as long as it makes sense, and then you can do the calculation based on that. All right, any questions? Now, might as well write down the random walk transition matrix, if you will. So this is really a one-dimensional random walk, okay? So a one-dimensional random walk, yeah, it has no cap on left or right? So okay, here's the thing. You could also have a random walk, but you basically only limit from 0 to 10, where you start with so much money, right? That's the initial fortune. And if you go up to 10, you quit and you call that a win because your opponent only has $4 or something like that. If you go back to 0, you lose and you are ruined, right? Etc. etc. Anyway, but that's also a random walk. But the random walk we have in mind in general has no cap. You can go from 0 to -1 all the way. So in general, right, just from any position, you can move to the right position with probability P, go to a left position with probability 1 minus P. That's a random walk. So the transition matrix, right, if you want to call it that, really has no starting place. You can only do a snapshot, right? Because it's really an infinite matrix, right? But what happens is what? Basically, it only has terms on the off diagonal, right? So like that, right? P1 minus P, and then P1 minus P, and then P1 minus P, etc. Okay, so that's the limit. Any question? So let's see, for the last 4 minutes or so, let's see if I can move on to 4.2. You know what? Maybe let's not do that. Let me actually go to the other one where this is the 1D random walk, the gambler's ruin problem, but it will be attached to the concept of absorbing state, okay, which is going to be a very useful concept we'll be using later on. A state I is absorbing if PII equals to 1. All right. So there you go. A state is absorbing if you cannot escape from it, right? Once you're there, you stay there. Okay. So I mean, in terms of if you want to draw a little graph, I goes back to I, right? With probability 1. Of course, you can move to I, right, from some other states. Whatever, right? But the point is, the moment if you move to I, you will stay there. So in the gambler's ruin problem, something like that happened. So, you know, as I was telling you, right, basically there are two states, either 0 or n, that represents a fortune of the gamblers, right? Where 0 means they're done, right? They lost all their money. N means the opponent's done, they lost their money, right? So no more game to play. In between, they can win back and forth, right? And let's say the person we're tracking will win $1, right? Move to the right with probability P, move to the left with probability minus P, they will lose $1 with probability minus P. So the transition matrix of this, right, will be 0 up to n, 0 up to n, but 0 and n will be absorbing. Again, the reason is, you know, basically you're modeling the situation where, right, the game stops, right, once you move to those states because no more game to play. So it's just one, right, at those states. In between, you have what we just say, right? So if you have one state 1 here, then you have P1 minus P, right, like that. And if you have state n minus 1 here, then n minus 1 move to n would probably P, and move to n minus 2 would probably 1 minus P, things like that. Right? So again, it's not that hard to write down the gambler's ruin, right, transition matrix. The concept really is about absorbing state, right? A state that is absorbing if, you know, once you move there, you stay there. All right, any question? All right, if not, then I'll see you next Monday. Okay, have a good weekend.